just wanted to read out something about returns to the origin that he talks about. And the first thing you should do is you should open to page 86 or 87 of Feller and look at this picture he has. This is an actual sequence of tossing heads, coins, heads and tails. Maybe he says he tossed, but who knows what he did. And this starts at 0, goes up to 10,000 tosses. Alright, and here the scale is in hundreds, here in thousands. And what you see are these sort of enormously long stretches, which take very long to come back. I mean, each one is like a return to the origin in our language. And the longest is about, in this particular sequence, is about 3,000 tosses. In other words, in a sequence of 10,000, you have 3,000 steps in which you don't return to the origin. I just wanted to make it plausible that the mean time of return is actually infinite.
What is the y-axis?
Y-axis is the the difference between the number of heads and tails. So if A is winning here and B is winning on the other side. And of course what's also interesting is what the paragraph he writes after that. So the original record contains 78 changes of sign. So square root of 10,000 is 100. So, there should be an order of 100 changes of sign. Now, you might think, okay, but look, on average, there are 100 changes of sign, and the spacing between each of them, the successive ones, should be 10,000 over 100. The answer would be 100. So that is not right. This is the part that is wrong. There are, in fact, 78 changes of sign. 78 is about 100, but the gaps between them are far from uniform. So there are lots of quick reversals and then very long stretches also. This is why the mean becomes infinite. Anyway, sampling of expert opinion revealed that even trained statisticians expect much more than 78 changes of sign. And nobody counted on the possibility of only 8 changes of sign in 10,000 tosses. He actually observed that. The probability of not more than 8 changes of sign in a sequence of 10,000 tosses, that probability is as large as 0.14. So 14% of all games will have only 8 times that you change. So it just tells you what a rare process it is to come back. If these records seem startling, this is due to our faulty intuition and to our having been exposed to too many vague references to a mysterious law of averages. This is right. I mean, 10,000 divided by 100 is 100. And you'll be, on average it's 100. That's wrong. Average of 1 over something is not the same as the actual. Okay, so just keep that in mind. Thanks. Okay, let's get to the main point of this lecture. And this is to deal with one of the simplest sorts of interacting particle systems. Sometimes this goes under the name of the exclusion process, and the system is very simple. Let's deal again with one dimension. Many of these things generalize to higher dimensions, but for class we keep ourselves to one dimension. And you have particles which sit on this 1D lattice. Here's a particle, here's a hole, here are 2 particles, etc. Each particle attempts a random motion independent of the others at rate u forward, at rate v backward. Okay, but the jump that's attempted can be completed only if the side that it's hopping to is big. But this is full, so even this attempts it can't. That's it. It's a simple rule. Now, the question is, what do you think will happen here? For instance, if you just imagine that you had random walkers, and now you will plot x this way and time this way. If you had a single random walk, of course, its trajectory would be something like that. Right? But here's a bunch of random walkers, each doing a random walk, with the constraint that this walk cannot cross the other, right, because of this exclusion. So as a result, each walker is sort of hemmed in by its neighbors. how will the root mean square displacement behave as a function of time? Okay, so clearly, if you start here and you wait a long time, it will have moved. So there are two ways of arguing, and both appear sort of plausible. One says that, okay, you know, what does it matter? Random walks is a lot of random walks is still be random and should be like the old one. That would suggest that root mean square was like t to the 1 half. The other argument is the following: that look, you have so many particles, there's a finite density of particles, therefore there's a finite mean spacing between them. Okay, so that mean spacing, no matter what, that mean spacing will stay. Therefore, you know, a given particle cannot move very much more than the mean spacing, maybe 10 times. In other words, you know, there's the other particle, there's the other one. Even at very long times, you know, how can it move much more than the mean spacing? Which would then suggest that as time goes to infinity, the excursion is finite. Well, neither of these is right. Turns out, and we will show it in some way today, the right answer here for a given particle is that the root mean square displacement actually increases as t to the 4. So I just wanted to tell you one answer before we proceed. Okay, so it is moving, and of course it can't exceed the others, but in some sense the whole bunch also moves. And how much the bunch moves determines this t to the 4. So this is the right answer. This is long. Okay, now let's, this is just a preview of something, but let's go about things a little systematically using the things we established yesterday. So, what we can therefore say is that W C to C prime, we have of course a master equation that describes this. Configuration C is this set of all occupation numbers. Curly bracket means you specify all. Okay. So C to C prime equals U if C prime differs from C by single particle volume. And it's 0 otherwise. Okay, so I'm sorry, this all, everything I said here was for the case U equals V. Symmetric problem. So let's for the moment consider symmetric problem. So this is called the symmetric exclusion process or the simple exclusion process. Okay. Now, in this symmetric case, it's clear that WC to C prime is equal to WC prime to C. Both are U. Therefore, in this case, for this special case, the W matrix is Hermitian. As we said in general, it's not, but in here it is, because these elements are equal. Therefore, the right eigenvector corresponding to eigenvalue 0 will be the same as the left eigenvector corresponding to 0. Implying is the steady state. Is this clear? Left eigenvector is always 1 on 1, and in this case, because the matrix is Hermitian, this is. So what does it mean? It means that every configuration is equally right. It may go a bit against your brain of thinking because it says that if all the particles are on one side, all the holes are the other, that's as likely a configuration as everything mixed up. Because somehow intuition says, and correctly, that the system should reach a state which is more or less uniform density. But, you know, this is actually true. And the reason this is actually consistent with our intuition is that a state like this, with everything on the left and right separated, there's essentially only one or capital L such states. Very few. Whereas random states, there are many. And it's the entropy of the states which determines which sort of state. But configurations, each are equally like that. So be clear on this. What is the total number of configurations? Let me call it script n, and that's equal to NCN, where n is the number of particles, n is the size of the system. And we will be usually interested in the limit n over L finite, in other words fixed density, and L going to. So very large system which you have a finite list. Okay, so good. Now for this system, what can we say? Well, so we've already noted that every configuration is equally likely. Every configuration with a fixed number of particles is equally likely. Now, this you can show. So it's also intuitive, but you can show it, and I will leave you to puzzle this out. So, okay, no, first of all, let me make another small point which is evident. So, detail balance is valid. Why? Because detail balance is WC prime to C equal to C prime equal to WC to C prime P of C. But we just said P of C prime equals P of C, we put that. And we also know that in this case W is equal, therefore detail balance is valid. So actually what we are describing is an equilibrium system. What is the energy of the system? Sorry? Or which one? No, we just proved it 2 minutes ago. We proved that this is a right eigenstate. Here is C, here is C prime. Everything is equally like. Sorry? No, this is a stochastic model. I mean, there is no average velocity, symmetrical. Yeah, there is no energy. So energy is zero. Actually, the energy is zero. So let's just take off from it. So detail balance is valid. The energy is zero. E of C is zero for all C. For all allowed C. There is no distinction. Therefore, we can immediately do our usual thermodynamics with impunity. So let's calculate just for fun a grand partition function. Now, of course, we are dealing with the system with a fixed number of particles, so really speaking, we should use a canonical answer. But as usual, it's discrete. If you have a large system, it doesn't matter. Large equilibrium system, it won't matter which answer we use, and so we'll use a grand canonical. Therefore, grand canonical answer, the partition function, will equal sum over all configurations, and we need not restrict ourselves to any subspace with a given number of fugacity. This is e to the beta mu to the summation ni again n times e raised to minus beta energy, but the energy is zero, so that's 1. So this is it. Okay, actually let me go back and make this. These are non-interacting particles. Okay, so here we are. I mean, sorry, non-interacting in the sense that each side is independent of the other. These are interacting particles, right? So what does this give you? This gives you a product over sides. Partition function at each side. Okay, let me complete this. Sum over ni, that side I, of z raised to n. But what are the allowed values of n? They are 0 and 1. So this is a product over I. 1 when z is 0 and so ni is either 0 or 1, so you get 1 plus z. But this product is identical to this becomes 1 plus z raised to n. So this is your grand partition. If you like, you can determine the density immediately from this. So rho is equal to well, you can just work it out. It's appropriate derivative is set to z, and let us write the outside terms of z. So rho is simply z over 1 plus z, which you can invert if you want. And well, you can do that in component to dividend, right? That's how you find rho in terms of z. But more interestingly, 1 over beta d rho by d mu, which is related to the compressibility. This is exactly compressibility. I keep forgetting something like compressibility. Yeah. Okay, this one is equal to rho times 1 minus. Also, we can find the equation of state. What is the equation of state? It's the relation between pressure, density, temperature. How do we find that? Pressure is easy to find once you know the grand partition. You take a log. That's it. So if you do that, you just immediately derive beta p equal to log 1 over 1 minus 2. Okay, so this is the equation of state. Sort of instructive to plot the pressure versus density. And what it looks like is that at small rho, you can expand the log and it's linear. That it has to be. It's like an ideal gas. So P is rho kT. But then the effects of exclusion come in. The largest rho can be is 1 in this, and the pressure actually diverges in some way. So you have to squeeze into apply a very large pressure to accommodate for all this. Okay, so these are all simple equilibriums to distal mechanical reductions that you can make. Yeah, so this is a very good question, and in fact this was going to be one of my exercises for you. What is the meaning of temperature in such a system? You have entropy, clearly, and the free energy is U minus Ts. U is 0, the free energy is minus Ts. How do you relate to temperature at all? So just think about it. And one way to think about any such, this is not unique to exclusion process, it's true for any system with only hardcore interactions. You have no energy in the system. How do you think of temperature? So one way to think about it is to put the system next to another system where temperature is well, for instance an ideal gas. So think of a hard core system separated by a wall and an ideal gas on the other side, and the temperature of the ideal gas will determine the position of the piston, which will in turn determine the density, and something will happen. So please figure this out. It needs something. It's an important question and it should be answered by you. Okay, so I have it written here as an exercise that is okay for you. Alright. Now, in the large system limit where we are using the equivalence to a grand canonical ensemble, we can clearly write the probability of occupation of site I, the probability of Ni, as rho times Kronecker delta of Ni 1. It's just writing something in longhand, which is very obvious. It's just saying that if you have a large system and you focus on site I, ask whether the site is full or empty, what weight will you give to that occupancy? The answer is that you will, if it's occupied with probability rho. Okay, so that's the, if it's occupied, this fires and you get rho. If it's empty, that happens with probability 1 times. I just wanted to write it. Okay. This is true in an infinite system. independent of any other site. Therefore, in an infinite system, if you look at the correlation function Ni Nj for I not equal to j, this will factorize into Ni Nj. In other words, what I am saying is that the probability, I should have written this earlier, probability of Ni, I mean you used this already somewhere, is the product over this line should have preceded that. So the full configuration probability is given by a factorized form like this, and a form like this is known as, as you might imagine, as product measure. So for this system, in the thermodynamic unit, you have product measure. When you have product measure, things simplify because the occupancies are independent and the correlation functions therefore are trivial. So as a second exercise, work this out in a finite system. So in a finite system, show that Ni Nj, again for I not equal to j. So by the way, I equal to j is very simple. When I is equal to j, you have Ni times Ni, that's Ni square. But since Ni can be 0 or 1, Ni square is equal to N. Therefore, for I equal to j, you just get rho for this product. But for I not equal to j, prove that this is equal to number of particles L into N minus 1 divided by L into N. So if you subtract off minus average of Ni and j, then that will of course be this minus N by L the whole square. And if you plot this function, what it says is that it is negative everywhere as a function of I minus j. It's the same value and it's negative. Why is it negative? That's part of the meaning. What is the meaning of negative? Obviously it means some sort of anti-correlation. But just figure out what it is. And it goes away in the thermodynamic limit. This gap is proportional to 1 by L, and as L goes to infinity, this becomes 0. So please work this out. And first of all, work out the answer, and second, prove that understand it. So, okay. So today what I want to do is really talk about the symmetric exclusion process, also about what's called the asymmetric exclusion process. It's a little complicated to do it because in the end one has one behavior, in the end the other has another behavior. But on the way there are many things that are sort of common. So if you don't mind, I'll keep switching between the two. So when you write your notes, it will not be very symmetric exclusion process and then asymmetric. It won't be like that. It will be symmetric, this part, then asymmetric. I think it's good because you'll also get used to thinking about the two systems. Okay, so at this point, having said all this, let me turn to the asymmetric. It will turn out that many of the things I've put here will just hold as they are. Some of them won't hold. Many of them will hold, but you need a different proof. Okay, so let me, for instance, this will not be true, that will not be true, nor will this. We'll come to the right answer for root mean square velocity. It's a little subtle, it depends on the value of rho as to what this power is. I mean, in case you're curious to know, I'll just tell you. So the root mean square. So this is like a preview. I don't even know whether we'll get to prove everything about this. But for the so now let us come to the asymmetric exclusion process. For me, it's very simple. Let us start as A. Asymmetric exclusion process. I put back a V, and I write here U not equal to V. That for me is the. So you may have to write something. Okay, now what will these world lines look like? They will be similar, except they'll all be tilted. Each particle will have a tendency to move right. So it will move. Nothing will stop it except its right hand neighbor and its left hand neighbor. So we have a bunch of world lines that actually go right. The slope of the world lines, mean slope, will define the drift velocity. And we'll work out in 3 minutes what is the value of the drift velocity. Okay, so let's go ahead. Anyway, now let me come back to this thing. So obviously x squared is not a very meaningful thing to look at when something is moving with the drift velocity. What we should look at is the deviation from the drift velocity. So let's x minus, suppose drift velocity is v. And ask for this. Now v is the drift velocity. Yeah, is there a question? Sorry?
He's getting problem.
Oh, okay. No, that's why I put subject. V subject. Okay, we need to do something else, but let's call it V. We won't call it C, because it turns out there's a new speed in this problem. That is what the one will cause C, which is not equal to. Now, this one, you might think that what you're doing is you're doing a Galilean shift, you're moving with the main speed of the particle, so therefore now it's back like the symmetric extrusion. So that turns out to be totally wrong. It's not that way at all. And the answer here is that this in fact goes like t to the power 1/2. If rho is not equal to half, and it grows like slower if rho equals half. So you might suppose that class now we'll come back to rho equal. I mean this power quarter, you don't come up with the new powers, it will be 1/3. So I'm just citing the answers. So you know the answers in case you cannot get to the proofs today. So this is what happens. And we'll try to understand at least why rho equal to half is different from rho not equal to half. But these are the answers. So this we should do. They're not difficult to understand, but after a while. Now, okay, let's see. So I'm moving along with the ASAP, and I'm modifying the fewest things. Now, some people are looking very puzzled. What is
So
that?
rho not equal to half is just a random walk by
Well, for rho not equal to half, it's t to the half. T to the half is also the value for random walk. But I'm not implying that this is because it is like the signal. It's just this. I mean, I'm not implying a causal relation. What I've written is correct. In fact, I don't know of a simple causal relation. In some way, yeah. Not in an obvious way.
Can you give an expansion?
It is more related to the following thing. Since you're asking, let me just say. Okay, so should I let this equate out? Yeah, okay. So let me tell you all this. This is sort of going to build up. What happens in this system is very interesting. Okay, so again, we were supposed to prove all this, and we will, maybe after lunch. It's like this. So suppose you look at your system. Like this, and suppose you mark out the density. Now, this is a system with more or less uniform density, but so it's statistically uniform. But even so-called uniform state will have some bits of higher density and lower density. Some just statistically, and you'll make out some difference between light and dark. I'm trying to show. So here's a giant compression. Here's a direct action. Okay, this will just happen. You just, randomly populate something and you'll find that this happens. It turns out what happens in the system, if you evolve in time, is that these patches of density, basically, all these patches just move. They move around. They move at a speed which is not equal to the speed of the particles. It's a different speed. So if you watch these things, they sort of go like, so this thing will go like that. go like that. To some zeroth order transmission.